Hello and welcome to TidyX episode 98. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick, at Tidy_explained is the both of us on Twitter, as is tidy.explained@gmail.com, where you can shoot us a message, or you can open up an issue on the GitHub repo, or probably the most common way is to go on YouTube, like and subscribe, and drop a comment at the bottom. And if you enjoy our work and you want to support us, we do have a Patreon page. So if you'd like to go over there and buy us a coffee or a beer, we would gladly drink it.
we love hearing from you all. We love getting the feedback that y'all are enjoying what we're doing. This really helps us figure out content to keep on moving forward with, or like, oh, this is kind of dead, let's maybe back off from this. But yeah, so this is now episode 2 in our series on sampling, simulation, and intro to Bayes. So that's quite a heady topic that we've got going on here. Last week we had introduction to the various base R distribution functions that exist and the various prefixes of PQRD. And a bunch of all the distributions there. I thought it was really helpful for me to learn a little bit more about those as Patrick was talking about that. Hopefully you all did as well. Let us know in the comments down below. But now we're going to go a little bit more into the first piece, sampling and simulation with R. So let's get this thing started. Patrick, do you have anything to share as I go to share the screen?
Yep. So before we get into Bayes intro next week, it's important that we take this first week and talk a little bit about simulation and resampling, because those are going to be incredibly important going forward, because a lot of times what you're trying to do is simulate from a distribution or build simulations of data. And so these things are really critical, and R does an awesome job of making these things approachable for you, which gives you a ton of flexibility over the models that you build. So you don't have to just take data and run it through a function that says lm y tilde x, data equals dat, and get a summary output. You have some flexibility over these things, and R makes this approachable. So this is our first step into that. And we're going to talk about simulation and resampling, and we're going to set the table with a few key definitions so that we make sure that we don't confuse ourselves around these things. So the first is going to be simulation. And simulation and resampling, sometimes people use these words interchangeably, but they are two different things. Simulation is a random generation of multiple samples from a defined data generating process. So the defined data generating process might be like a mean and a standard deviation, a sample size and a probability of success or failure. Resampling is different, because resampling is that new data is simulated by resampling with replacement from the actual data set. So in this case, and we're going to show an example of this. If it doesn't make sense right now, don't worry. In this case, you actually have a data set. And what you're going to do is you're just going to continually resample from that data set for n number of times and build a much larger data set. So we're using that resampling process to create the data. So two different things. Simulation, we're defining a data generating process, and then we're generating a data set. Resampling, we have a data set, and we're just randomly plucking points from that and creating a new data set. The mean, we all know the mean is the arithmetic average. It is the measure of central tendency that we'll be using here. Median is another measure of central tendency, but for this purposes of this one, we're going to talk about the mean. The standard deviation is probably the more common or most common measure of dispersion or spread of the data relative to the mean. So this is actually like the spread of the data within the sample that we're looking at. The maybe less common or less talked about version of dispersion would be the variance, which is the standard deviation squared. So if you have the variance, you take the square root, you get standard deviation. If you have the standard deviation, you square it, and you get the variance. And then one other measure of dispersion that we haven't talked about yet, but we will, is going to be precision. We'll talk about that later on, which is 1 over the variance, or the inverse of variance. Standard error is the other one we're going to go over today. And so this actually quantifies the accuracy of the sample measurement relative to a population. So for example, for the standard error of the mean for a sample of a data set, this represents the potential standard deviation of that mean in the population. So if you think about it like this, our standard deviation is a representation of the dispersion of spread within the sample. The standard error is a standard deviation, but it is the standard deviation of the means within the population. So basically what we're trying to infer here is we're saying we have this sample of data set, and from that data set, we have observed this certain level of dispersion. And so we want to take that dispersion and we're going to divide it by the square root of the n number of data points within that sample. And that's going to give us our standard error, which is helping us try and identify the accuracy of this measure when we try and infer back to a population. Okay, so that's standard error. So
lots of fun stats topics right here.
It works a lot easier if we actually try and sort these things out. So let's go through resampling first. Yeah. So resampling, you love the sample function. Take us through it.
All right. So the sample function. So we're going to start out with a normal vector, a numeric vector of some random values that we just picked out of a hat. 4, 2, 7, blah. And so we generate this. We now have D. So this is now a numeric vector that exists. And we're going to use the sample function to do this. So sample can take in a X, which is a vector, a size, which is indicating the number of samples that we want to pull from it, and replace is saying, well, you can pick from the same spot, or you can repick the same value. Or not. And so if we're in our situation, we do want resampling because we want to be able to, well, in the future, we will want to be doing this. So in this case here, we're saying replace equals true, which means it can pick from the same position in that vector twice when it's trying to pick 5 different values out here. So we can run that. And so it's going to pick out these 5 random values. We can run it again.
That's a perfect example there, because 1 was selected 3 times. However, in our data set, it's only represented once in position 1, 2, 3, 4, in position number 6.
Yeah.
So the resampling went through, and in this example, each of those values has the same probability of being selected. So we haven't added a weighting to it. We can add a weighting to it, but you wouldn't do that for the bootstrapping. So we're not going to do that here.
Yeah. But this is how you could define the probabilities of the various entries in the vector D. The probability that you want of grabbing that first entry is 0.1, and it normalizes across all the values that you enter in there.
Yep.
So just so you can see what it might look like, and I am botching
there
it.
You go.
So we were saying that more often than not, we're probably going to pick this 5th entry, which is 10. And so you can see 10 got picked a bunch of times.
Yeah. So not super useful for example here, but incredibly useful if you're building data simulations where there's like a higher probability of a certain outcome than another. You can weight it.
All right. So that's sample.
So that's a little bit about sampling. Let's jump into what bootstrapping is. So bootstrapping is drawing multiple random samples from the observed data with replacement, which is exactly what we just did in the above chunk. The draws must be independent, and each observation must have an equal chance of being selected, which is what we did in the above chunk. And the bootstrap sample should be the same size as the observed data in order to use as much information as possible, which we did not do in the above chunk. So we set our size to 5. In this case, in the above chunk, if we wanted to do a bootstrap of this, we would type in length D and lowercase d. Yeah. And so now, and then you run it again and you get all these different numbers. We're just selecting the same length of the sample. Every one of those values has the same chance of being selected, and none of them are dependent on each other. So we're just pulling that information. So that's what the bootstrap is. So let's look at an example. So our friends over at profootballreference.com, we went over there and we got Peyton Manning's completion percentage during each of his NFL careers. And I just manually typed those into a vector for us. And so we can run this and we can use R's built-in functions to get our measure of central tendency. So on average over his career, he was a 65% passer with a standard deviation of about 3.3%. How many years do we have? We have 17 observation years. He missed a season due to injury, I think. So he had 18 career years. And then here's our standard error. So it's the standard deviation divided by the square root of the number of samples, divided by 17. And that gives us a standard error of 0.8%.
So running out the logic.
Standard,
Did that.
Yeah.
There
cool. So we could create a histogram of his each season. So this is a histogram of Peyton Manning's completion percentage across each of his seasons. So we see it's a bit left skewed. So the skew is where there's few. It's on the left side with more data towards the right. So there's a few years where he was below average, particularly his rookie year where he threw a lot of interceptions. And then his last year when his neck was kind of failing him and he didn't have to throw the ball downfield as much. Those were and then majority of his career was up towards that, above 64%, 66% range. Okay, so let's create a bootstrap sample of Manning's career. So we're going to set our seed at 3. We're going to set the length because we need that for the bootstrap. We have to take the length of our equal length of the resamples, and we're going to run 1,000 resamples of Manning's career. And we're going to create this this little vector of NAs for storing values, and then we're also going to create this boot set list. Ellis, why do we want to create a boot set list?
So the reason we want to do this is if we ever wanted to come back and be able to recreate the bootstrapping that we just did, you'll want to keep all the indexes that you are using to identify your bootstrap sample. So rather than this kind of going off into the ether, we could always recreate this because it's actually a semi-random process with the set.seed. This makes it a little bit easier, so you don't have to rerun and recalculate all the things or all the boot sample indexes. All you have to do is just rerun and get the index. And so this is valuable. In this situation, it's kind of trivial because we're only dealing with a small vector. But in the future, if we were to be dealing with like data frames, and we were actually sampling rows out of that data frame, and you want to make 1,000 boot sets out of that, you're now replicating your entire data set 1,000 times. And so that can get really chonky and big. And so this would be a really quick way. So if you want to rerun something, you don't have to have a massive data set. You just know, okay, I'm going to rerun over these indexes, and pull out the values again. And so it's just good for storing. It's good practice.
100%. So, all right. So we're going to run this bootstrap. So we're going to set up a for loop to do this. And so in each observation of that long 1,000 point vector of NAs, we're going to run through that vector 1,000 times. We're going to run through this for loop and store those values in that vector. So we're going to use the function that Ellis just introduced us to, which is our sample. And remember, for bootstrapping to work, we need to take the total number that we have of the observed values. In this case, it was 17. So we're going to have to sample 17 observations with replacement equals true. And we're going to store those. So we're storing indexes here. We're basically storing a vector of row indexes. We're going to save those row indexes in the boot set list that Ellis created. And then what we're also going to do is we're going to take each of those indexes and go to our original data set, the Manning data set, and say, hey, Manning data set, get me those indexes that I just pulled out, the 17 indexes that I just pulled out with replacement, and calculate the mean of them and store that in the boot Manning vector and do that 1,000 times. So the bootstrap is a mean of means, right? It's a sample. We're going to take a mean, and then we're going to take the mean of those means to get the outcome. And this can be done for any parameter. It's not just means. You could do it for standard deviations. You could do it for odds ratios, et cetera, et cetera.
But I see what you mean.
Yes, you see what I mean. There you go. So it runs pretty quick, and now we have a whole bunch of Manning simulations, 1,000 Manning seasons, where we've resampled from what we've observed, and we can plot these and take a look at them. All right, there's the original, and there's the new one. So you can see the new one is filled in a bit more. It's a bit more normal. than around, it's a bit more normal, right around 65% relative to the opposite version. And this is one of the reasons when people do bootstrapping is they have a small sample that they believe in the population should be normally or is normally distributed. And so the bootstrap helps us to push the data into a more normal type of looking sample. And we'll see why that's important here in a second. And what else? We have from our observed results, we can also then calculate things like our mean. This is the original data, standard deviation, standard error. We can calculate the 95% confidence interval. So remember, for the confidence interval, it's the mean plus or minus your standard error multiplied by the critical values, which we're basically saying we want the critical values for the inner 95%. So that's why P is 0.025 and 0.975 on the high end. And then we could look at the bootstrapping. Now, I did make a note here, which is important to keep in mind, is because the bootstrap sample that we created is a mean of means, when we run standard deviation on this, because the standard error is the standard deviation of our means, when we run the standard deviation on this bootstrapped vector, what is being returned is the standard error. We can confirm that by running this and seeing that it will equal something similar to what we had for the standard error in line 85, and we're pretty darn close. If I want to get this back to the standard deviation, I need to do a little bit of algebra. So remember, standard error equals standard deviation divided by square root n. So if I multiply both sides by square root n, I now get standard deviation is going to equal standard error multiplied by square root n. And so now we're pretty close again to what we observed above, and then we can run our quantiles on this data. So above I used the Q norm data because I had an observed mean and standard error. Down here I have a vector of data, so I'm just going to use the quantile function over that data and pass it the inner 95%.
So running these, so I'm also going back
try to run them in parallel. Yeah.
Next to each other.
And you could see they're relatively close. So people are going to say, well, what's the point? Who cares? If they're relatively close, who cares? Here's the thing. A lot of times we're dealing with a sample that is small, and maybe there's limitations around getting a larger sample. Maybe it's expensive to get more people. Maybe it's difficult to get more people. Maybe whatever we're doing research on is maybe a little bit risky, and we don't want to risk people to whatever it is we're trying to do research on. Yeah, exactly. So you might have a data set that's small and it has this big outlier in it. The bootstrap can help us get a sense for what we think might be happening in the population because we create new samples from resampling the data. So here we have a bootstrap sample. We're going to set our seed. We're going to set it to n equals 5.
Yep.
And we are... Actually, it should be 1, 2, 3, 4, 7. Sorry. Yeah. There we go. 6. Okay. So we have data that has an outlier
7.
now. Oh, 7.
Not bad.
There we go. All right.
We're not good at math.
Bad counting day. So we have a data set now that has a sample data set that has a whole bunch of numbers close to each other and then one like really absurd outlier. And so if we run the mean on this, the mean is very sensitive to that outlier. It gets pulled towards it. And notice that the mean and the standard deviation are nearly identical. And we can plot the histogram of this, and you're going to see that it's going to look kind of wonky. Okay, So we got this one outlier point, and everything else is concentrated down below number 5. So let's try and use the bootstrap to help us. So Ellis, you want to take us through this bootstrap?
Sure thing. It's pretty much the same sort of thing that we did before. So we're going to create our boot.dat vector, which is we're going to create through rep, which stands for repeat. We're going to repeat NA, n boot times. And so you can see that it's just a vector of NAs. Now for every I, or for every boot that we're going to be doing, I is representing that from 1 to n boot, so that's 1,000. We're going to take a sample of the 1 to n from the vector that we want to be, get the indexes from that vector that we want to be pulling from. And then we're going to do like we did before. In this case, we're not going to keep the boot set because we know we're not going to be using this in the future. take the mean of the data set of dat and drop it into boot dat at location I. And so because we pre-allocated everything, it runs lickety split. And so now we've got this new data set here. As you can see, there's some cases where it clearly grabbed the 15 a couple times, a couple places where it didn't. So that's how you resample that. So now we can take a quick look at this data set, the original one. So we're going to do par so we can get the two plots next to each other that you've seen. Do a quick hist of dat. Let me spread that out so that we can actually see it. So this is the original guy. This is the mean that we calculated of the original data set. Now let's do the hist of this new boot data set. As you can see, it's now handled that, that outlier a little bit better. And now we can regenerate that mean as well.
Yep.
And it looks to
and that's going to have, and now it's going to have some ramifications. We can see a substantial amount of the density of the data is now at 5 or below 5. And this will have ramifications now on the mean and standard deviation. So if we look at our original data, so remember the mean and standard deviation are relatively the same. And we get these massive confidence intervals.
Yeah.
And now we take the boot, okay, mean, standard error, standard deviation, and our quantile intervals. How far off are we? Oh, sorry. So we've constrained some of the data, and we could run as many, resamples as we want to do. The idea is to get a better estimate or a closer estimate of what we think in the population without having to go and snag a whole bunch of new data sets.
So I just ran this for 10,000 because the for loop.
And it runs like really fast. Yeah.
We can see it's not.
So now we can see that it starts to come down even. It starts to get constrained a little bit more each time that you rerun your reset.
Because it's an outlier. It's less likely to grab it.
Less likely to grab it, yeah.
There we go. All right. So that's how it handles outliers. But let's go
simulation.
through the simulation one. How do we actually use this, Patrick?
All right, simulation. So remember, we're creating data from a data generating process. So here we have a baseball hitter, and we want to know how many hits we would expect in 500 at bats for a hitter that is a 250 hitter. So he's basically getting a hit 0.250 a quarter of the time. So we set those parameters, and we can run this in our cool R binom function that we talked about last week. That's going to return the observed number of hits, the observed number of successes, given the parameters, which are the probability of success, which is 0.25, and the sample size, which is 500. And we set n to be 1 because it's only one season's worth of data. So if we divide that by the number of observations, we're going to get returned some batting average that should be relatively close to 250, and given some random margin of error because we know there's lots of uncertainty. The probability of hitting exactly 0.25 is going to be low, and there's just as much that you could hit 0.24 or 0.26. And so that's only one simulation. So let's create a bunch of simulations and see how much distribution there would be. Like, what if we ran this at 1,000 times? How much variability in performance would there be? So we're going to simulate 1,000 seasons or 1,000 simulations of one season at 500 at bats with a batting average of 250. We're going to, again, allocate some space to storing the results. So we have 1,000 NAs, and we run our simulation, which is doing exactly what we did above. And that gives us a whole bunch of number of hits, which, again, if we divide by our at-bats of 500, we're going to get the probabilities or the batting averages. So there's our simulated number, our distribution of hits.
Mm-hmm.
And then the right side is our distribution of the batting average, the player's batting average. So now this takes into account the uncertainty. So we can, again, produce our summary statistics over this. We get our mean batting average, and we get our standard deviation of batting average for this is since this is a proportion, it's the square root of the where did we go? Square root of the probability of the outcome multiplied by 1 minus the probability of the outcome divided by sample size, and that gives us a standard deviation. And then from that,
we can ignore that.
Yeah, it does that sometimes. From that, we can get our 95% confidence interval. So we have a mean and standard deviation. We can run this. And so we're somewhere between 0.224 and 0.278. And we can also get this is just an alternative way to get the confidence interval. It's going to produce the same thing with less code and less math. We could also get the quantile interval because we have a vector. And so the quantile interval is going to be the quantiles that's going to be larger than what our confidence interval is. Mm-hmm. And to finish up, we didn't need to do the for loop. It was probably overkill. We could have just done this with our binom by setting the n to 1,000. So basically saying we're going to do 1,000 seasons of 500 at-bats with the probability of a hit being 0.25. We could have done this in one line of code. The only reason why I wanted to walk through the above is because we're going to use that type of stuff later on when we go through other Bayes simulating. So simple thing here, and we could hit the mean, and we get something very close to how many at-bats we observed.
Yeah,
there we go.
Very, very close. So it's not like we're not like totally changing the structure of the data. We're just re-inspecting it multiple times.
Yeah, correct.
That's an important thing to get. It's not like it's going to magically give you new things.
No, the only way it would give you new things is if you changed some of the parameters. Like you had reason to believe that the player really wasn't a 250 hitter and maybe he was a 230 hitter or something like that. Like or changing the number of at-bats, right? Changing the number of at-bats would be the other one. It's like, how certain would you be of this player given a certain number of bats? And we can look at that kind of stuff and as we get into our Bayes type of...
It's almost like that was a setup.
Yeah, well, it was, yeah. because that's the idea, right, is that what we're looking at here is very clearly defined parameters that have no caveats around them. Bayes is going to help us sort out some conditional probabilities. So given this, this, and this, what would we expect to occur type of thing?
Yep.
Type of questions.
Exactly. Yeah, but that's how you can start doing sampling and simulation and making your boot sets and whatnot with some very simple functions that exist in base R. You don't even have to go download a new package to do that. So there you go.
That's it.
So thank you all so much for joining us. As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick. And we are both on Twitter at Tidy_explained. Tidy.explained@gmail.com is where you can shoot us an email. You can open up a issue on the GitHub repo. You can, and we appreciate it if you do, like and subscribe to the YouTube channel, and you can drop questions, comments down below. And if you enjoy our work and want to support us, we do have our Patreon page where we will drink whatever you care to donate.
Thank you all so much, and keep on enjoying your world and exploring it.